comes back with an image that you can order as a t-shirt or something like this. But the core of that is a very simple, there's no database behind that. There's no really results to come back to. The only thing about it takes a few seconds. So maybe it's not a snappy thing, but overall it's a fun little website. It works well. So there's a state list. Do I have state? Does my output depend on anything other than some input that's directly coming in from a web request? There's the number of visitors you have, the amount of traffic you have. When a visitor arrives at your website, how many requests are involved? Do you have static content? MyPyDay and Image Identify both have some HTML pages, some normal web front-end static content, and then they have some active content in the back. The active content is mostly what we're interested in. That's where our server-side Wolfram language code lives. But when you're developing a web app, you do want to think about what's my static content. If you have state, then how much data are you talking about? You have a site like, an enormous site like YouTube where there's a vast quantity of data, and any particular video you want to view has to locate it, has to start streaming it. So the Image Identify site has the ability, once you've uploaded some image that Image Identify has never seen before, and it works on it, it runs some recognition on it, and it comes up with a result. People might like to share it, either because it's ridiculously wrong or because it's cool. So the sharing of it is interesting. With MyPyDay, you share your result. It's probably acceptable for somebody you share with to spend a few seconds recomputing. Image Identify, we don't want to do that, so we store results. So you want to start thinking about, when I'm writing my applications, am I storing results? How are those being retrieved? And then there's a question of, there's another aspect, which is concurrency. I post my link to my great thing I developed. I get 50,000 visitors all at once. Can anything go wrong? And for some things like MyPyDay, the answer is the only thing that would go wrong is you overwhelm the cloud somehow. Now, our public cloud is designed to auto-scale, so the more demand we get, the more nodes are put into service, and there are some being held in reserve, so it all kind of works well. But if you have interactions between your users, if you're writing a social networking site, then there's some contention to think about. How do you handle that? There's an interesting architecture for tweet a program. The idea of tweet a program is I tweet at a certain Twitter user, Wolfram tap, and the content of my tweet is taken as code to be run in the Wolfram cloud. The way that works is you've got a background task running in the Wolfram cloud that is continually asking Twitter, is anybody talking about me? Is anybody tweeting at Wolfram tap? And from that input gathering mechanism, it will spawn out handling individual tweets. So an individual tweet is found, and then this background task makes an API request within the cloud to handle the tweet and get our content. I was going to really start with a motivating example, which is this application that I worked on for a few hours last week, and there is, hopefully, I see a blinking cursor. I still don't see my mouse pointer. So what we've got here, I've published this chat site. It's in the talk notes. If you want to go here right now with your laptops, it's wolframcloud.com/objects, and my username, jfklein, jfklein/cloudchat/chat.html, and I've got a shortened URL if I could get to my talk. All right, so what just happened when I typed help? My JavaScript code got an event. It did an AJAX call to the Wolfram cloud, uploaded the content of my chat, server side added it to a data structure. A JavaScript script requested, are there any new chats, and fetched my new chat from there, from the server. So it was round tripping. If people are really piling on here, then then we would see, we would see more activity. If there was a lot more, we would be seeing, constant updates. So this is an example where we have lots of users, lots of API requests going on. This is not your MyPyDay where there's a single calculation. This is more about, moving data back and forth. So there's some interesting things we can do here. I will, now that I've got this back, I will actually, no, let's go to the source. So I've put the source up here so you can take a look. The server-side code, I want to show what's happening there. So when a new chat comes in, this write chat function, all we're doing, the way we're storing these chats is in a single .m file that's got a bunch of associations one after another. So when we read chats, we're doing a read list. We're getting in a list of associations. There's our data. The associations are on the JavaScript side are JSON, so they're easy to work with. But here's where we're creating our data. And there's not too much to it. There's an ID and the time zone. The time and time zone are interesting. The time is being normalized to GMT here. When you request the chat, your request is being localized by the kernel. So if you're in France, actually, if we're here, we're already seeing that this is doing what it's supposed to do because these times should be local to Champagne. So when we're retrieving it back, we localize these according to the current time zone. So time zone for the requester is always set to where they are, what their geolocation is. So we have an opportunity to add some things here. We could add things about, based on some metadata that we have about who's calling. We could add their geolocation. We could add what country and city they're from. We could look up entity properties about where they are. So there's this simple little app might give you a lot of ideas about interesting ways to extend this or interesting places to go from here. I thought of conversation starter mode where it randomly picks an entity property about your country and says, there are 23 million phones in my country. What about yours? So there's lots of things we could do here. So I will, since we talked about these properties a little bit, and we referenced some of the applications. One thing I didn't mention was DataDrop. So a couple words about that as an example of an application. So that's too small. Okay. I don't know what happened to the style sheet because I definitely worked on the style sheet to make these all bigger, and they're not bigger. But that was easy. So DataDrop. You can almost think of it as a service or as a platform that you can build other things on. DataDrop, there you have the idea that you have connected devices, Internet of Things, and they or anything you want to build can put data into a data bin periodically, however you want, and then retrieve it. So here you've got an idea of it's definitely stateful. An input that you give into it, like get me the contents of my data bin, does not depend on just the input. It depends on the state of your persistent store, your backing store, what's in the bin. So it's a little more complicated. There was a blog post from Wolfram recently after we got some new coffee machines in the office, and they came with these nifty little cartridges where you could pick a flavor. So the idea was, let's give people a way to rate these flavors. And the Flavor Rator app has a couple interesting things about it. First of all, the input is gathered by a form. So you fill out this form, you pick, which flavor, we didn't like the French roast. Sorry if I'm messing up your data, our node. So what that form did when I ran it is it dropped my selection into this data bin. The data bin's now collecting information from all the users that visit this, and that output was generated by visiting the entire bin and summarizing it at once. So that's good when you've got 50, 100 people in the office that try this out, but that doesn't scale super well if you're taking political surveys or something like that for millions of people. So something you might need to think about as you're designing something like this is, gosh, I might need to aggregate as I go, have a scheduled task that runs through my data and does summaries like this, or every time I drop something in, update a mean, a median, something like that. So these are the types of things that I'm hoping to get across. And we talked about tweet a program. So I wanted to spend a second looking at, now the magnification is killing me. So we'll go back for a second. There's a lot to say about the model, the environment that you're programming in. And this picture is worth quite a few of those words about the model. This is very basic. On the left, we have a variety of clients that could be coming from a variety of different sources. Browsers, Mathematica Desktop counts as a client, as like the cloud, export, cloud, deploy. Those commands are all clients that hit the cloud. Mobile device counts as a client. And on the right side, we have a model of the cloud. So let's just trace an interaction. Let's say we ran our coffee Flavor Rator just now in our browser. So this red line represents that a web request came into the cloud. As it hit the cloud, it hits a load balancer that looks to see, have I heard from this user before? The IP address and so on are taken into account, and what cookies are coming in with this request. If I see that there's no session cookie, I create one. Once a session is created for a user, sessions are routed to the same node in the cloud for the life of that session. So load balancer decides that this request goes to this particular node. Further requests will also go to this node. So here's a blow up here's the node detail. So we have a web server that request hits. It has access to several resources. It has access to kernels, Wolfram language kernels, has access to a local disk on that node, and also has access to a network available file system or a network available service that is accessible within the cloud. So there's a couple of things to point out while we're looking at this still. One is when you're thinking about latencies and time, one thing to be aware of is time from internet to the cloud, and another one is network time within the cloud. So in the case of something like tweet a program, you might have a background task doing work on one node that makes an API request within the cloud. That's going to be a lot faster than your connection. So these are all things I think you want to know as you're designing applications. So there are several kernel types. The ones that we typically care about when we're writing these web applications are the public and the service. Public is used for these cloud objects that are not static. So those would be the API function, the form function, delayed. We're getting some new ones. There's a grammar rule. So anything that requires evaluation goes to this public kernel type. And the service is for scheduled tasks and that family of things where it's not actually connected to web requests. You can create a scheduled task through the web, but when it runs sort of behind the scenes. There's no interaction with the browser or anything like that. So a couple things worth noting here. What node in kernel am I on? So we'll go back to Zoom. So you may have used machine ID, process ID to find out where you're running locally. If you do a cloud evaluate, this is very similar to running an API function. This runs on a public kernel. If I ask it to evaluate that in the cloud, I'm not connected, probably. It'll come back and tell you with some host name, some process ID. Now, if you evaluate that again, watch the process ID, you may get a different number. And if I run that repeatedly and tally them up, you can see that there were the same node, but 4 unique kernels. So this is just experimenting and discovering that model we were looking at before. There are several kernels on that node that are dedicated to this type of thing. The exact number here may change over time, so it may not always be 4, maybe a lot more, probably not less. And these things are all reconfigurable in a private cloud. Another thing worth noting is API overhead. I'm only mentioning it because I've spent so much blood, sweat, and tears over the past while working on this particular aspect. This is just, when you call an API function, how long does it take from the time it hits the cloud to the time your code is running? A year ago, that number was not so wonderful. Now it's pretty good, and you're not going to notice it. You're going to be seeing network latency much, much bigger than that overhead. Just a brief word about this because I think this has been covered pretty well, but when you think about writing your code and when it's running in the cloud, you want to be aware that you can use normal file operations, copy file, export. You can use normal file operations, and you can also use operations through cloud object wrappers. Your home directory files are accessible either way. Other users' cloud objects are only accessible through the cloud object wrappers. So one thing that sometimes happens, it is the case right now that the direct file system access is going to be faster than accessing through a cloud object. And if you've got anything that's sort of sensitive to time, you'll notice that. So a strategy to deal with that is, if you've got a cloud object that's going to live for a while, create it as a cloud object and then update it or read it directly through a normal file system operation. So in my chat application, the backing file that holds the chats was created as a cloud object sort of when we created the chat room. But then after that, just read list, normal file operations. And just a debugging note, a couple things can go wrong when dealing with cloud objects. Content can be wrong, so anything that you're used to, examining the content of a file applies to cloud objects. You can file print it, you can run get, you can run binary read list if you're suspecting like new lines are wrong or something. But meta information can also be wrong. The MIME type, I cloud put an API function, and when I try to retrieve it, it doesn't run. Well, the mistake there is cloud put just creates an expression, and that's marked as an expression by its MIME type. And if you look at the MIME type, you'll see it ends in the word expression. If you cloud deploy an API function, it ends in expression.api. It's that expression.api makes all the difference. It makes the difference between serving it as an expression that's just some text and running it as active code. So Do look at options of a cloud object and cloud object information, which has even more information about a cloud object. I should mention the kernel sandbox. If you try to access a file that's not in your home directory or sort of one of the temporary directory or one of these things that's sort of yours, the kernel will act as if the file doesn't exist, even if it's there on the server. Trying to import the password file, the kernel just acts like it doesn't exist. And generally right now, running binaries that you provide is not allowed. And I wish that were not the case. We're looking at ways to get it so that we can have a secure system that you can, that you can be sure that you're protected from a malicious user, but at the same time allow you to do things like use the compiled functions, C accelerated compiled functions. We can't do that in the cloud right now, though. I'm going to skip the rest of this and just point you to the cloud execution metadata guide page, because I want to leave time for at least one question. So I'll end there.